Okay, as I saw my A group on, hey everybody, I saw on my A group yesterday, we talked about on Wednesday with my A and B group, I was B at home, was focusing on just the parameters of radioactive isotopes, half-lifing, and I went over the video a little bit explained. But what I'm going to do is kind of recover that and do some sample problems that will lead into what you'll be doing today here on Thursday, whether you're in the classroom with me or my A group at home, that you'll be doing that I'll post on Schoology. Okay. But the biggest thing is I want to just reiterate again is the importance of what half-lifing does. Half-lifing gives us that order of operations, or that place in which artifacts, fossils, whatever might be found in Earth's history or whatever, that we need to put a sequential date with it and put it in its right respectable order, whether it be the evolutionary history of Earth, geological time scale, when something happened, when something ended, when something appeared, when something went extinct, whatever it might be. But the isotopes that are naturally occurring, like I said yesterday in the notes, coming from the periodic table, have certain levels of decay. All of them are different. Some of them are better than others to use. But I'm just going to show you once again in format here again and do some sample problems for you with also the margin for error as well. So I'll do probably 3 or 4 different problems here, and then I'll cut you loose that you can work on these on your own for Thursday, Friday type class, okay? All right, so first things first, remember, we're talking half-lives, for example, all right? We have various different isotopes, half-life, okay, whatever it might be. In simple retrospect, like I used the example of carbon-14 has a shelf life of 5,730 years, okay? So remember what it was saying yesterday when I talked about that. That means that the sample of carbon-14 found in whatever structure that we're abstracting it from, we know that the half-life of carbon-14, okay, takes 5,730 years for half of that sample to decay, break down, disappear, change, whatever you want to call it, okay, like the hands on the clock. And we know every time the cycle of 5,770 years takes place, that it goes through another half-life. So half of whatever of the sample goes each time, right? So, i.e. example, if I had a fossil, all right, that went through 3 half-lives, and I wanted to know how old is it, okay, how much of the sample's left, or even if I was given in grams, how much of the actual mass is left of it. I'll use this as a little example before I actually put a problem up here and go for it. So if I said 3 half-lives, 3 half-lives, I can write it out this way. That's 1 half-life, 2 half-lives, 3 half-lives, like so. 1, 2, 3. And a lot of times you can do this in your head, but I'm just trying to, all right, which takes 5,730 years. I know this looks repetitive, but, like I said, the more I can break it down for you, all right, I would make sure that you got it ingrained so we don't have to worry. So that makes sense. So we know every half-life takes 5,730 years, okay? All right, and that sample, if this was doing little objects, if this was, prior to it, 1 half-life of this, if this is the sample of it, half of it is gone. So that leaves me with half the original sample. After 2 half-lives, I had this already gone, half of that leaves me with 1/4. And if I was going through 3 half-lives, here, that was gone, that's 1, that's 2, that's 3, that would leave me with 1/8. Well, how did I get that number? 1/2 times 1/2 times 1/2 gives me 1/8. So that gives me that ratio there. Phew, if I got that. And same thing, 1/4 and 1/2. And if I asked how old would this fossil be after 3 half-lives, just take 5,730 and add them up or times it by 3. 5,730 times 3 equals. So if this was a true fossil, we would know that this carbon-14, if it went through 3 half-lives, was 17,190 years old, okay? That's how we knew that if this sample, whatever it might have been, went through 3 half-lives, half, and each time showed you little visual things, gave you the percent, okay, gave you the total and things of that nature, even told that. Or what if I told you this particular carbon-14 was, obviously this is its half-life, that's the given, and went through 3 half-lives. So let's say the sample was 100 grams in size. Whoops, 100 grams in size. Let me get my, here it is. Oh, hold on, let me get my towel here. If it was 100 grams in size, okay, so it started out as, let's say I had a 100-gram sample, and just add this in here, okay, right? And when it finally started decaying after 1 half-life, well, it's pretty simple. If that's what I started with, after 1 half-life, obviously, it's going to go in half, so that leaves me with 50 grams, okay, after 1 half-life, which took 5,730 years, went from 100 to 50 grams, okay? The second one, now if it went to a second half-life, I just half this again, so half of 50 is 25 grams. So after 2 half-lives, that sample went from 50 to 25. And if I wanted to know the size in the metric unit, of grams, half of 25 is 12.5, okay? 12.5 grams, okay? So that would be the answer if I asked you how much of the mass is left from the original sample. You give me my answer in that. If I asked you how old it was, it'd be a total, okay? Or maybe I gave you the total and went through 4 half-lives. How long is each, so they're like word problems. I'm trying to show you all the various different ways in which you can solve that, whether it's how much of the ratio is left in percentages, how old total is it, or if I give you the total and I ask you, how long is each individual half-life, or if I gave you the amount of the sample and it says at the end of X amount, how much is left, okay? So those are all the different ways in which you're plugging in, but the bottom line is you will always have the enough amount of information for you guys to solve the problem, okay? So I just kind of, in a roundabout way, showing half-lives, and once again, why is this so important? It gives us exact, well, that's not pretty exact, but pretty darn close. I used the example yesterday in class. I said, okay, if you were running like a sprint, okay, and I had a stopwatch, and it's pretty accurate from point A to point B. You cross the stopwatch, and I say you ran a 6.8 60-yard dash time, okay? But if I had one of those electronic ones that they do at like combines and stuff that gives it to the hundredths of a second, and as soon as you cross and break that beam, it's more accurate. It's kind of like that, all right? So radioactive dating would be like using stopwatches, which is very accurate, but not super precise as opposed to, that. So when it gets it within a certain margin of error, and that's what I'm also going to teach you with the sample problem here in a second, how to do percentages, and remember that, because as much as I thought you guys remember that, you need a refresher on that to what the answer is asking. And this still goes back to chapter 1. What is the question asking? Just answer that, okay? All right, so I'm going to erase this one, and I'm going to do a sample problem up here. Ouch. Ow. Ow. Yeah, that hurt. Get my finger on that. Ow. Yeah. Ow. Oh, that did not feel good. Okay, no big deal. Small problem. All right. So, troops, okay. So, my problem states, I think I'll uncover it here. I think this is the one I was going to give you. Yeah. So, see if we can, I'm going to turn off the other light here so you can see that top problem I'm going to do right here. I'll scoot up even a little more. Okay. Yeah. We'll do this problem right here. I'm going to turn off the light so you can see it even better. Okay. Okay. So, what this problem is stating, it says the half-life of carbon-14 is 5,730 years old, as we know. If a mammoth, that's like Manny from Ice Age, has 1/8, so right off the bat, 1/8 of carbon-14 to carbon-12, because that's what it breaks down to, and 1/8, in my head, I should be able to do that. 1/2 times 1/2 times 1/2 would be, 3 half-lives. If I have 1/8 of carbon-14 broke down to carbon-12, what was it thought to have when it was frozen in the Siberian glacier? How old is the mammoth? Okay, so I'm looking for total age. And then it's asking us, and this is a normal thing, and at an air level of plus or minus 10%. Okay, so we're going to do that. So, first things first. It says 1/8, which we should know is 1/2 times 1/2 times 1/2 is 1/8. Okay, so that's 3 half-lives, all right? And we know that 5,730 is 1 half-life because it tells us right there. So I just can times this by 3. So my simple math here is, so I don't get right here, is 5,100. Come on, calculator. Oh, I don't have enough light in here, do I? Let's do it this way. Okay, there we go. 5,730 times 3 equals 17,190. Okay, yeah. Which I thought that's what it was. I just didn't want to rewrite it wrong here. 17,000 years old. So what this was saying is it answered this first part. How old is the mammoth? Boom. I just answered that because 1/8 was there, which was 3 half-lives. Okay? 1/8, 5730 times 3, so that. But then it asks you a second part. What is the air level at a plus and minus 10%? Okay, so I'm going to take this total when it asks you that, 17,190, and I've got to figure out the plus and minus 10% of it. So I take this total, 17,190, and to get the plus, all right, I'm going to find out what is 10% of that, okay? So I go to my calculator, people, little flashback, times 10% would be, if this is 10%, boom, it does times 0.1. You can do that in your head, but if you can't, 17,190 times 0.1 equals 1,719. So we know that 10% is 1,719 years. Okay? That's equal to 10%. Math 101. So it asks for the plus or minus, so I'm going to take this base unit, 17,190, all right, and the plus and the minus. So I'm going to take 17,190 and add this to it. 17,190, 17,190 plus the 10%, 1719 equals, so that tells me that 18,909 years, that's the high, and then I'm going to take that base and say what's the 10% margin low, 17, once again I'm kind of doing it here so you can see it hopefully on the calculator, 190 minus the 10%, 1719, and that gives me 15,471. 15,471 years. Okay, so what does that mean? The high and low? They're saying the maximum and minimum age of that fossil, of that mammoth, it was frozen in the Siberian glacier. It walked Earth, Manny, walked Earth somewhere between the almost 19,000 and 15,500 years ago. That's that margin for error. That's pretty darn accurate. That's the example I've given you using a stopwatch as opposed to maybe a digital laser stop for hundredths of a second. Okay, that's pretty good. So when it asks for that plus and minus percentage, remember, you're going to take that total, find out whatever percentage. If they asked for 12%, you would have found out what's 12% of this base and done the add and subtract from the base. If they said 15%, find 15% of that. 5%, okay, so it's the same thing. Take the base, find the percent, add that to the base for the high, subtract that from the base for the low. Okay, so that's how you do the plus or minus if it's a two-part question. Okay, all right. So on this one, once again, so recap, carbon 14 breaks down to carbon 12, 1/8 is left. We had 3 half-lives. Each half-life is 5730 times 3. That's the total age, roughly. Then it asked for a margin for error plus or minus, so I found out 10% of that, which was 1719. I added that to the base to get the high. I subtracted that from the base to get the low. So I know my fossil walked Earth, Manny, the Siberian glacier area was alive sometime in that time frame. Boom, done. Okay, that's that sample problem. Okay, next one is using potassium 40, which is right below it. I'll scoot it up just a smidge here. Okay, on this problem, or scoot it down, no big deal. All right, so now we're looking at, cover this up so I can write. All right, so we're looking at this problem, even real simple too again. All right, that was the second sample problem I'm going to give you. So the half-life of potassium 40, okay, which was also the main one they talked about in your notes, and I talked about a little bit to my A group, and then of course you watched that. Potassium 40 is such a great popular K40 because it has a long shelf life. If you have a hard time, it'd be like a Jolly Rancher compared to cotton candy. Cotton candy dissolves real quick, like something like this, but potassium 40 takes a lot longer for it to break down. So it has a shelf life. They rounded it up. It's actually 1.26, but 1.3 billion years. That's fine. So if I have a rock specimen, right? I have a rock right here. I'm going to do a little visual aid here. I got a 1 gram rock sample, 1G, of potassium 40, K40. Why do you keep writing K40? Because K is a symbol on the periodic table for potassium. Okay? When it was formed, how much potassium 40 would be left in the rock after 2.6 billion years? So this is the total, 2 billion years ago. Billion years old. Okay? All right? All right? So, 2.6 years. So obviously if 1.3 into that, that's 2, which means basically that rock is 2 half-lives old, right? 1.3 is 1 half-life. They say the total age is 2.6. Simple math in your head, or not, whatever floats your boat, okay? But it's asking for how much is left. So I want to know how much of that 1 gram sample is left. So they're asking for mass. Pretty simple, all right? So if I started out with 1 gram, and I don't went through 2 half-lives, so after the first half-life, this went from 1 gram to 0.5 grams, right? Okay? And then it went through a second half-life, which halved the 0.5 again to 0.25 grams, right? Done. That's how easy that was, okay? Once I identified what the problem was asking, it was asking for how much of that sample, 1 gram left. There's the answer, 0.25. Now, here's a mistake a lot of times you guys will make, is you'll count the given as, oh, this is 1 half-life. So you would say, oh, 1 gram after 1 half-life, and then you have 2 half-lives. Even though you understand the point, I've seen a lot of times that you're always off by 1 half-life because a lot of time we take the given or the start of the problem, we count that as the first half-life. Remember, that's what you start with. So when it goes through 1 half-life, have the original sample, and from there. So check your math. I see it all the time. And it happens. It's one thing on a worksheet where we're just practicing. I got it. Oops, made a mistake. But if it's a test, you only have 3 problems, and it's 10 points, 47% of your grade. You miss 1 problem, you go from an A to, 66%, okay, or something of that nature. So it just doesn't take long. We solve that problem in milliseconds, okay? So make sure you check that. All right. All right. So that's the second sample problem I did for you, okay? And that was actually using the ones that was right out of the notes, meaning the samples carbon 14 and potassium 40. Okay, so I'm going to do one more, okay, on a different thing here. So, all right, let's do, this is just a random one here, no big deal. So, dun, 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 dun. Oh, man, screwed my page. There we go. Okay, so you can see that there. Scoot it up, cover up the rest so I can write that confusion. Okay, one more sample problem and we're all good here. All right, so here's a whole different, like I said, there's so many different isotopes. Some are better than others, but I'm just giving you random ones, all right? So the given ones, if I have a half-life, I have a 100 gram sample, 100 gram sample of nitrogen 16, N16, okay? There's that isotope, all right? That decayed, broke down all the way to 12.5 grams, right, of the nitrogen 16. And each half-life, okay, it did this, all right, it decayed to, and it did this from here to here in 21.6 totals, in a total of 21.6 seconds. That was fast. If you blink and it's passed, all right? So it wants to know, what is the half-life, okay? So I'm working like this word problem backwards, right? So I'm a visual person, that's so, okay. If I have my 100 gram sample, start with, all right, I'm just going to keep having until I get to this number, all right? So, and then I'll show you. This is how I would do it. There's more than one way to do it, math, but like I said, simple is easy as well. So 1 half-life puts me at 50 grams. 2 half-lives, have it again, gives me 25 grams. 3 half-lives puts me at 12.5. Oh, that's the number I'm looking for. So, it must have went through 3 half-lives in 21.6 seconds, right? So all I got to do is take 21.6, right, and divide that by 3 into that, which I believe my quick math is 3 into that 7, and 3 into that is 2. So it looks like each half-life of nitrogen 16 takes 7.2 seconds. Okay? So that's a different way of solving it. It's all the same stuff, but it's practicing again. What's it asking? All right, it's giving me the information. Everything I need to solve it. And this particular one gave me the total, wanted to know how long each half-life was. I had this to start with. This is what it broke down to. I made it simple. Okay, started with this, 1 half-life, half. Then I halved it, then I halved it until I got to what I was looking for. That was 3 times. Okay, so I went through 3 half-lives. 3 into that. Divided this up. 7 equal increments there. If you want to check your math, just add up 7.2 plus 7.2 plus 7.2 is 6. 21.6 seconds. Boom, same thing. Ding, bam, boom. Check my answer. 100% right. Okay? So there's 3 types of problems. Same stuff, same format. Okay, for you guys to keep the, if you need references for that. All right. So then what I uploaded is, I think it's 16 problems for this first go around on Thursday. All right. That you will work. All right. Various different isotopes. It doesn't matter what the isotope is. All the stuff given there for you to solve, and you'll just solve for the answer. Okay. So simple math, division, multiplication, whatever it is necessary like that. Okay. So these 16 problems that I'm uploading that obviously for October 7th here. Here's the samples to help you work through some problems. You can watch this as many times you want, stop, go, whatever, okay? And there's 2 short worksheets, 10 and 6 problems on them that I've attached below, okay? All right, you got any questions? Obviously my A group will see this, my B group will see this, and they can ask me here in class or headphones to watch it. My A groups are at home, did great yesterday, should be self-explanatory, but if you got any problems, all you got to do, reach out to me, okay? All right, have a great rest of your day or whatnot. This is Thursday's work, all right? So I will talk to you and update and see you all virtually, B, A group on Friday, one way, shape, or form, and then of course B, I'll see you for the first time tomorrow, and we're good to go. That's a wrap.